Okay, so recording is done. It's being recorded now. Okay, so in complex numbers, we saw that any number x plus iota y or a plus iota b, whatever, these are complex number where x and y they are real numbers and iota is square root of -1. That's how we define it, right? So any number that is written as a real number plus iota times another real number. Usually we write 3 first iota afterwards, but no issues. -2 plus 7 iota, -3 iota, right? Etc. These are all complex numbers. Um, we also saw that these numbers and the points, if I have a point xy in xy plane, right? If this is x, this is y, the height, then of course this is your point. So we have a one-to-one correspondence. So we can say that for every point xy, there is a complex number x plus iota y, right? So there is a R square is a simple plane where we have set of all points xy such that xy belongs to R. And set of complex number is set of all numbers of this form x plus iota y where xy belongs to R, right? So see, they are almost the same things, similar things, right? So So it means R square and C, they have one-to-one correspondence. Means for every complex number, there is a point, and for every point, there is a complex number. Okay. Two things. So we can say that this vector is basically your complex number Z. We can draw from 0 to this point P. If P is any point whose coordinates are xy, then OP vector can be represented by a complex number z is equal to x plus iota y. This is called Argand diagram. If I write different uh, complex numbers on xy plane, we call it Argand diagram. This is x-axis, this is y-axis, right? So if you want to write, let's say 1, 2, and this is 1, right? 1, 2. So this is the point 1, 2, 2, 1. So this will be a complex number 2 plus 1 iota, like that. Okay. Or if you have another one, let's say 1, 2, -2, and let's say, or -1 and 1, 2, -2. So this point. -1, -2. So this, because this point is -1, -2, right? Then this vector will be -1, -2 iota, right? So it's etc. So we can draw many things like that. So see here, 2. All right. So these are your Argand. Drawing a complex number on Argand diagram. We had defined many things, Z conjugate, Z modulus. Two things that are important is this. If you have any complex number going from 0 to xy, then it has a length which is r, and it has an angle theta that is made with the x-axis, positive x-axis. Okay, so these r and theta are basically the modulus of z, that is x square plus y square root, right? And theta is called the argument of z, which is tangent inverse y by x, right? Because you see, this height is y, this is x. So tangent theta from here is y by x, perpendicular over base. So theta will become tangent inverse y by x. And this is a Pythagoras theorem, x square plus y square is equal to r square. So from there, we get this. So this is called the modulus of z, and this is called the argument of z. So if you have a modulus and argument, we can write the polar form. You remember when you have x, y, theta, then in polar coordinates, x can be written as r cos theta and y can be written as r sin theta. So these r and theta are also the coordinates of the same point, which are called the polar coordinates. X, y are called Cartesian or rectangular coordinates. It is from calculus now. It is not nothing from linear algebra. These are called Cartesian or rectangular coordinates of the point, and r theta are called polar coordinates of the same point. Okay, polar coordinates. So this is the relationship between x and r theta. So see, your complex number was therefore, your complex number was x plus iota y. So I can write x as r cos theta plus iota y as r sin theta. So I can write r as common. So inside you got cos theta plus iota sin theta. This is called the polar form of a complex number. Okay, this is called polar form of z. Right? So this is that is x plus iota y, and this is the polar form of z. Let's say if, for example, if z is 1 plus square root of 3 iota, right? Then r will be mod of z, which is 1 square plus square root of 3 square. So 1 plus 3 is 4, so it will become 2. And theta is argument of z, which is tangent inverse y by x, square root of 3 by 1. So if you do that, it will be tangent inverse square root of 3 is, I think, pi by 60. 60, yes. Let me check. Tangent inverse square root of 3. 60. Pi by 3. Okay, because here you have 1 and square root of 3 is more than 1, right? So this is square root of 3. So this is your point. This is your complex number that is equal to 1 plus square root of 3 iota. So see that this is 60 degrees, right? 60 degrees can be written as pi by 3 radian. So therefore, the polar form of z is equal to r, which is 2 into cosine pi by 6 plus iota sine pi by 6. Okay. There is another thing which can be used to find the powers, which is called De Moivre's theorem. I think Moivres. De Moivre's theorem. De Moivre's theorem says that if you have cosine theta plus iota sine theta, if you have this complex number and you take any power of that, then you can just multiply theta by n, cos n theta and sine n theta. Okay, so basically this n comes down here. If you have a power n, this n goes to this theta. So see how easy it is. Otherwise, it's very difficult to take the power of a complex number. For example, let's say if I have cos theta plus iota sine theta power 2, let's say, right? Then I have to take the square, a square plus b square plus 2ab, right? A square. Here iota square is -1. You see, iota, because iota is square root of 1, right? So iota square will be -1. So I can replace iota square here, -1. This is -1. So I got cos square theta minus sine square theta plus here iota into 2 sine theta cos theta. So these are the formulas from trigonometry. Cos theta square theta minus sine square theta is cosine 2 theta, and 2 sine theta cos theta is sine 2 theta. So you see here, when I took the power 2, right? When I took the power 2 here, it automatically goes in with theta. 2 comes here, right? So this is true for, it is a proof for n is equal to 2. For n is equal to 2, this is the proof, right? But we can accept it for 3, 4, 5, because for 3, 4, 5, 6, it will be very difficult to prove it. So we can just accept that this is true for any n. For any power n, this is true. Okay. So let's see in the previous example. When z was 1 plus square root of 3 iota. If the question is find z to the power 10, see how difficult it will be. Z to the power 10 means 1 plus square root of 3 iota to the power 10. Now it's difficult. There will be 11 terms. 1 to the power 10 plus 10 into 1 to the power 9 square root of 3 plus I don't know what number here is. Then 1 to the power 8 square root of 3 square, and keep on going. At the end, you will get 3 to the power 10. So it's not that easy. And with iota as well. Then there is iota with it, iota square, iota power 10. So a lot of things are going on. Difficult, right? And if you don't remember the formula for power 10, then you will multiply. Maybe you will take the square first and multiply square with square to get z4, then 4 with 4, 8. So a lot of things will be going on there. Instead of that, if I write the polar form of z, if I write the polar form which I just got, 2 into cos pi by 6 plus iota sine pi by 6, right? This is the polar form of the same z in polar form. If I write this in polar form, I have this one. Now, if I take z to the power 10, it is 2 to the power 10 and cos pi by 6 plus iota sine pi by 6 to the power 10. And now, if I use De Moivre's theorem says that this power will go down with theta and down with theta here, right? So basically, you got 2 to the power 10 cosine 10 pi by 6 plus iota sine 10 pi by 6. Very easy. No need to open that a square plus b square plus c square, so on. No need to do that using De Moivre's theorem. So what I did here, I used De Moivre's theorem. That makes our life very easy. Now cos 10 pi by 6 will be cosine 10 into pi, which is 180 by 6. 10 into 60 I can write. And 10 pi by 6 or pi by 3 was there. I think pi by 3. It was pi by 3, sorry, not 6. It was 60. You see, pi by 3. So I don't know why I wrote pi by 6. This is pi by 3. 10 pi by 3. And here it is also pi by 3. So 10 pi by 3, 10 into 60. So that is minus half. And plus iota sine 10 pi by 3 gives you minus square root of 3 by 2. And 2 to the power 10. So here, see, 1 by 2 is common here. So I can write minus 2 to the power 9, and inside you will get 1 plus square root of 3 iota. So see, getting the power reduced to this one. If you want, you can check that. If you want, you can check like this, what I did here. Or maybe you can take the square because square is easy. Then you can go to Z4, which is multiplying square with square. And then you can multiply 4 with 4 and get 8. And then at the end, you can get Z10 by multiplying Z8 with Z square. So if you perform 1, 2, 3, 4 different products, you will arrive at Z10. And you can check that this Z10 will be the same as this. It should be the same as this. If you want the longer way, you can do that. So see, polar coordinates can help us getting different. Even if they ask me z to the power 100, let's say if they ask what is z to the power 100, I will take 2 to the power 100 cos pi by 3 plus iota sine pi by 3 to the power 100. So 100 will come down, right? 2 to the power 100, it will become 100 pi by 3 plus iota sine 100 pi by 3, because this power comes with the angle. So if I do sine 100 pi by 3, it gives me minus square root of 3 by 2. It is still minus square root of 3 by 2. And cos 100 pi by 3 is minus 1 by 2 again. So I got 2 to the power 99 minus 1 minus square root of 3 iota. Okay. So see, you can get any power, no issues. Power 49, 99. So the finding the powers is very easy. If you look at this angle, when the angle argument is 60, let's say if this is the argument, then if I continue, if I don't stop my theta here, continue and come back to this one, it will become theta plus 2 pi, right? Adding 360 angle. This is still give you the same vector, right? If I take one more turn and come back here, this will become theta plus 4 pi and so on, right? So it means not just theta, theta plus 2 pi, theta plus 4 pi, they are all arguments of z. So in general, theta plus 2k pi, where k is 0, 1, 2, 3, 4. 2k is even number. See, 2 into 0 is 0, so only theta. 2 into 1 is 2 pi, so theta plus 2 pi. Then 2 into 2 gives you 4 pi and 6 pi and so on. So these are all the arguments, but only this theta is called argument with a big A. We call it principal argument. You see here, I wrote the small a here. So with big A, we call it principal argument. This is the principal argument. And if you keep on adding 2 pi's, they are also the arguments of z. Okay. So if in the previous example, let's say pi by 3 was theta, but if I add 2 pi in it, it will become 6 plus 1, 7 pi by 3. This will also give you the same answer, no issues. You will get exact same answer with that as well. Okay. So sometimes we can use this polar form and De Moivre's theorem to solve the equations. For example, if someone asks you solve z cube minus 1 equal to 0, let's say, or I can say that, let's say solve z square plus 1 equal to 0. You know that there are no real solution for that, right? Because it is there is no z whose square can be -1. But we know that z square equal to -1 if I take the square root plus minus square root of -1, and that is iota. So plus and minus iota are the two solutions. Okay. So see, if you draw a circle, this is plus iota, this is plus iota. Iota is with y-axis. This is minus iota, and this is 1 minus 1. So see, two roots are on the opposite side of a circle. Let's say if I try doing this, z square equal to -1, right? And I write -1 as in polar form. So you remember -1 is here. This is -1. So you know that the length is 1 and the argument is 180, which is pi. You can see that r is, because -1 is -1 plus 0 iota, right? So r from here will become minus 1 square plus 0 square. So that is plus 1, right? And theta is tangent inverse of 0 over -1. Tangent inverse 0 is, if you use calculator, it will give you 0, right? It will give you this, theta is equal to 0. But you know that it is -1 in the denominator. It's on the negative x-axis. So we can add pi in theta. 0, pi, 2 pi, 3 pi, all are 0, right? 2 pi, 3 pi, so on. But I will pick this one because this is appropriate to my complex number. My complex number is not here. It is not 1, right? Where theta is 0. It is with -1 on the opposite side here. So here theta is pi, not 2 pi or 0. Okay, so that is the polar form. So my polar form will become r into cos pi plus iota sine pi. Agree? Now, if I take the square root on both sides, then it will become cos pi plus iota sine pi to the power 1 by 2, right? This 2 will go there and becomes 1 by 2, right? So I got this one. Now, De Moivre's theorem says that this power goes with the angle. So 1 by 2 pi plus iota sine 1 by 2 pi. Now cos pi by 2 is 0, sine pi by 2 is 1. Answer is iota. So you see, I got one of the roots. I got one of the roots. Negative iota is not there, but I got z is equal to plus iota. One root is there. So where has the second root gone? So what I can do, I can pick another argument. This was the principal argument. This was just theta. Theta was pi. It was principal argument. Another argument is theta plus 2 pi. If I add 2 pi, this is another argument which becomes 3 pi. So I can write another polar form, which is cos 3 pi plus iota sine 3 pi. Because that's after 2 pi, we have 3 pi, and 3 pi also give me the same direction, negative x-axis. Pi, and adding one more 2 pi, this is 3 pi. Okay, so now if I take the square root, so this 2 will go there, becomes 1 by 2. So now if I bring this down, it becomes 3 pi by 2, 3 pi by 2. Now cos 3 pi by 2 is 0 and sine 3 pi by 2 is -1. So I got another root, minus iota. So see, I got two roots now, plus iota and minus iota both. Now both roots are found. You can say that, okay, why do you stop? You have another argument 4 pi, which makes it 5 pi. So why not write another 5 pi? What will happen? Your roots will start repeating. You will again get iota minus iota, iota minus iota, iota minus iota. Okay, so first few values will give you all the roots, other will be repetition. So if you use theta plus 4 pi, which is pi plus 4 pi, 5 pi in your answer, then you will again get z is equal to iota. Theta is equal to 7 pi will again give you minus iota. So they will keep repeating. Iota minus iota will keep repeating. So that's the reason sometimes we need these arguments, not just the principal argument, but the general arguments by adding 2 pi in our principal argument. So there is a question, very famous question. They say find cube roots of unity. Finding cube roots of unity means, so basically, what does it mean? It means find, so let z is the cube root of unity, right? This is what I want, right? Cube root of unity. Unity means 1. So if I take 3 powers on both sides, it is z cube is equal to 1. So basically, our question is finding cube root of unity means find z such that z cube is equal to 1. Or we can say that solve z cube equal to 1 for z, right? Any question? So this is what we are looking for. So here, if I do what I did here, if I just directly do it, directly do this one, then I will not get 3 roots, because if I take the cube root on both sides, it is just cube root of 1, and that is just 1. Only 1 root. If I'm solving a cubic equation, there should be 3 roots, right? There should be 3 roots altogether. Three cube roots should be there because it's a cubic equation. So where are other 2 roots? Where are other 2 roots? This is the issue. Okay, so what we do, we use that method of writing 1 as your, so let's say this is your 1. So my length is 1 and theta is 0, right? So I can take theta 0 and then come back. I can take theta 2 pi and again come back, take theta 4 pi. And why only 3 values are enough? Why I took 3 values? Here I took 2 values only. In the previous example, we only took pi and 3 pi, only 2 values, because there were only 2 roots for the equation. Now I have 3 roots, so I will take first 3 values. 0, 2 pi, 4 pi. So I can write with theta is equal to 0. R will remain 1. R will not change. R1, theta 0. So my z cube will become, z cube is 1, and 1 can be written as r into cos 0 plus iota sine 0. Right? Now if you take cube root, so it will become cos 0 plus iota sine 0 power 1 over 3. 1 over 3 goes inside, so cos 0 by 3 plus iota sine 0 by 3. But cos 0 by 3 is 0, so cos 0 is 1, iota sine 0 is 0. So that is 1. So this is the same one that I got, 1 root, right? So see, real root is there. Now I will take r1 and theta 2 pi. If I take this one, the second choice, case 2, right? So my z cube will become 1, but 1 can be written in polar form as cos 2 pi plus iota sine 2 pi, because now I am taking the argument as 2 pi. So now z will become cos 2 pi plus iota sine 2 pi to the power 1 over 3. Now if you bring 1 over 3 inside, 2 pi by 3 plus iota sine 2 pi by 3. So 2 pi by 3 is 120. So sine 2 pi by 3 is square root of 3 by 2, and cos is minus 1 by 2 plus square root of 3 by 2 iota. This is what you got. Okay, and now the third case is r1. R is not changing because it is the length, theta 4 pi. So I can write z cube as cos 4 pi plus iota sine 4 pi. And when I take z, which is cube root, one by 3. So 1 by 3 will go in. So again, de Moivre's theorem says that 1 by 3 will multiply with theta inside. So now cos 4 pi by 3 is cos 4 into pi by 3 is minus 1 by 2. This is minus 1 by 2. And this is sine is minus square root of 3. So I got minus half minus square root of 3 by 2 iota, right? So these are the remaining two roots which were hidden when I tried to solve it directly. You see, when I tried to solve it directly by taking the cube root, I only got one root. So these two roots, hidden roots, are now I got this one, right? So 3 cube roots of 1 are 1 minus half plus and minus half minus square root of 3 by 2 I. And see, if I draw them in the circle, they are equidistant from one another. This is 1 exactly here is a 1 plus 3 and 1 minus 3 iota, right? So this is minus 1 half plus 3 by 2 iota. This is minus 1 half minus 3 by 2 iota. So same distance. You see this distance, this distance, this distance is the same. So they are the three roots on the circle, equidistant. So this can be done. This method can be used to find the roots of different values. You can find the roots of 2, 8, 27, whatever you want, you can do that, right? They can say that find the cube roots of 2. 8, let's say cube roots of 8, because cube root of 8 is 2. So that's why I'm writing 8. So 1 is 2, I know that. But where are other two? So I will write 8 in polar form, first of all, right? So whatever that is, you will write 8 in polar form and then use de Moivre's theorem. Now, why we only use these three values, as I mentioned you that the next three values are 6 pi, 8 pi, 10 pi. If you use 6, 8, 10, you will repeat the same values 1, 1 plus 3 and 1 minus 3. So next three values will exactly repeat the same roots. That's why we don't use them. We only pick the first three values. If you are having 4, let's say z to the power 4. Let's say you want to find fourth roots of unit, right? Then I will pick first 4 values of theta, whatever they are. One has 0, 2 pi, 4 pi, and I will take 6 pi as well because I have to complete 4 roots. So I will take first 4 values of your argument. So this was the question in the assignment that I posted, I think. So here, these are the complex numbers. Here you see, find the conjugate of z. You know what is the conjugate of z? If z is minus 5 plus 2 iota, z conjugate is minus 5 plus 3 iota. We just change the sign of iota. That's it. Okay. Write these numbers on Argand diagram. So I will take minus 7 here, 2 from here. So this is minus 7, 2. This is the complex number here, right? Very easy. Finding the mod and multiplication, division, everything is easy. These are main three questions that find the polar form of Z. Find the polar form, find Z20 by writing the polar form and then use De Moivre's theorem to find Z20, which I did, right? Similarly, find the cube roots of unity. I just did it, right? I just did this for you. The problem number 8 is done here. This is question number 8 from the assignment, right? And assignment 3. All right, I think that's if you look at let's say any other where is the assignment here? If you want something here, adding is not a problem. You add 2 in 3 and iota in iota. That's not an issue. 2 plus minus 3, right? And then minus 5 and 4 iota. Minus 5 plus 4 iota. So you add, this is minus 1 and this is minus 1. So minus 1 minus iota is the answer here for the first one. Multiplication, you multiply 1 with both, simple. So 1 with 2 and 1 with iota. Then you will multiply 2 iota with 2 and 2 with iota. So 2 iota with 2 will become 4 iota and 2 iota with minus iota becomes 2 iota square. Iota square is minus 1, so this will become minus 2, right? So 2 minus 2 and plus 2, because this will become plus 2. So 2 plus 2 is 4 and minus iota plus 4 iota is 3 iota. So multiplication is also easy. In division, yes, this division is, I did it last time, but let's say 3 minus 5 iota, 2 minus 3 iota. 3 minus 5 iota, 2 plus 3 iota. 2 minus 3 iota. It doesn't matter, plus or minus is the same thing. So let's say this is the complex number division, how to divide two complex number. What we do, we multiply by the conjugate of the denominator. What is the conjugate of the denominator? We change the sign and this is the conjugate of the denominator. So we multiply and divide by the conjugate of denominator. Now at the top, you have to multiply 3 minus 5 iota and 2 minus 3 iota. In the denominator, you have 2 plus 3 iota, 2 minus 3 iota, right? So now here I will multiply 3 with 2, 3 with 3 iota, then 5 with 2, 5 with 3 iota, right? So it will become 3 2s are 6 and 3 3s are 9 minus 9 iota. 5 2s are 10 minus 10 iota and minus 5 3s are plus 15 iota square. In the denominator, it is a plus b, a minus b. So it is a square minus b square. A plus b, a minus b is a square minus b square. So see, this iota is minus 1, right? Minus 1. This iota is also minus 1, iota square. So what you got? You got 6 minus 15, because 6 and this is minus 15. And they will add 9 iota, 19 iota. So 6 minus 15 is minus 9 divided by 4 plus, because it is plus 9. 4 plus 9 is 13. So this will become minus 9 by 13 and minus 19 by 13 iota. So see, whatever you are doing, your complex number always have this form. A plus b iota means real plus iota real. A real number plus iota, another real number. This should be your answer every time. So see here, we have a real number here, right? Plus a real number times iota. So real times real iota should be my answer. So that's how you can divide, multiply, subtract, add. Not difficult at all. So see, I have almost done all the assignment problems. So now it should not be a problem for you. You can easily do that. Okay. I think that's pretty much it for the day. I have one more. First part of this assignment, you see, is about, second part is about vectors. Okay. So next we will study about vector, some basics of the vectors, and that will be it. So vectors like ijk, which you have studied, we studied vectors in chapter 1 and chapter 2 as well. We studied as a column vector, column matrix, right? Like this. These are a vector in R3. We know that. And 1, 2 is a vector in R2 and so on. But we can also write vectors in this form, ijk, in ijk form. Okay, where any vector can be written as a1i or abc, ai plus bj plus ck, etc. I think you might have studied that in physics, right? Usually in physics we study vectors like that. So I will see how to add vectors, subtract vectors, multiply vectors, how to find angle between vectors, different things related to vectors, and using this form. Okay, that's what we will study, and that will take care of the first part of your second part, second 6 problems, 9, 10, 11, 12, 13, 15. Yeah, next 6 problems. So one lecture may be enough, or maybe 2 lectures, I don't know. All right. Okay, let me stop the video recording. So if you have any question, you can ask me after that.